All right, welcome. So we're going to finish up section 1.6, and then we'll talk about section 2.1 and 2.2 today. So let's finish up 1.6 here real quick. Where we left off was we started talking about inequalities, and we're just about to start talking about compound inequalities. So we are in 1.6. Get this 1.6, and this is linear inequalities. So a compound inequality is an inequality that is, well, it's two inequalities that are joined by and or. So we'd say and or joining two inequalities. Okay. So the difference between and or is if you have an and is the intersection of two sets, right? So if we see and, we're talking about the intersection of two sets, meaning the solutions have to satisfy both conditions. So we're going to have two inequalities that are going to come down to two conditions, and whatever your solutions are have to be the numbers that solve both of those conditions, or that make both of those conditions true, as opposed to or. And when you see an or, then it's the union of those two sets, meaning that your solution is all of those numbers that solve one or the other or both, right? So a lot of times you'll see and referred to as a conjunction. And then a or as the disjunction. So what do I mean by this? Well, let's take a look at a couple. Let's solve this. I have 2x plus 5 is less than negative 2x minus 15. Oh, I'm sorry. I'm reading the wrong one. I don't want that one. I apologize. That's gone. I want this one. There. Negative 3 is less than 2x plus 5. And 2x plus 5 is less than or equal to 7. Right? So we can solve each of these individually. A lot of people hate to see this x on the right-hand side, and if that's you, that's okay. Just bring it to the left. I'll bring it to the left just for simplicity's sake right now by subtracting 2x from both sides. So that would give me like negative 2x minus 3 on the left is less than 5 on the right. I'm going to add 3 to both sides. That gives me negative 2x is less than 8. And then, of course, when I divide by a negative, this gives me x is greater than, because I have to turn that inequality around, negative 4. That's one of the conditions. Right? If I solve the other one, I just subtract 5 from both sides. This gives me 2x is less than or equal to 2. Divide each side by 2, and I have x is less than or equal to 1. Right? That's my other condition, and of course they're combined now with the and between them. So the solutions to this conjunction is the intersection of these two things. It has to be the numbers that solve both conditions. So I'm going to draw both conditions out. There's one number line, another number line. Those are almost straight lines. X is greater than -4. I'll draw that here. And X is less than or equal to 1. I'll draw here. Okay. So these lines should match up. So like 0 should be at the same spot on each of them, because I'm going to end up taking them and smashing them together. But X is greater than -4. We'll just pick a spot to be -4. And again, it should match up. So -4 on the other guy should be there as well. But to be greater than -4, you can do an open dot, or you can do a parentheses if you like. But greater is to the right, so it's all of these guys over here. That's the visual, the graphic representation of what the solutions here look like, right? For my other one, X has to be less than or equal to 1. So 1 is here. Be less than or equal to, I'm going to fill in that dot or use a square bracket. But to be less than or equal to, then you're off in this direction, right? Now, if I compare these two, there's values in here, like say just random pick -2. -2 is in the filled in part on my top one and also on my bottom one. In fact, all of these numbers in between here are, right? So the values that are solutions to both are those numbers that are shaded in dark on the top line and those that are shaded in the dark on the bottom line, but they have to be shaded both places. So like a value like say over here that's say 3 is a solution to my top line, but it's not on my bottom line, so it's not part of the and conjunction here, right? So in fact, the very last line or the very last number to the right that is on both is 1. 1 is a solution on both of them, so I'm going to be able to go up to 1, but that's as far as I can go. To the left, I can go all the way down here. These numbers are all on both sides until I get to 4. And 4 is a solution to the bottom one, but it's not a solution to the top one. But it is that endpoint on my top one. So I'm going to write this as 4, 1, but a parenthesis around my 4, that indicates that the 4 is not a solution because it's not included in the top graph. And so interval form is 4, 1. All of the numbers between 4 and 1 and including 1 are the solutions to this conjunction. And again, you can think of it as taking those two lines and just smashing them together and see where the overlap is. And that's the overlap is from 4 to 1, not including 4, yes, including 1. Excuse me. So let's take a look at another one of these. Let's solve. Let me just blank this out here. Okay, so I want to solve. Oops, I want a marker. Solve 2x minus 5 is less than or equal to -7. Or 2x minus 5. I don't know why they're always the same expression. I don't know if I made this up or not, but it looks like I probably did and was not very creative. But that's okay. We're still going to solve it. On the left one, I'll add 5 to both sides. This gives me 2x is less than or equal to a -2. And if I divide each side by 2, this gives me x is less than or equal to -1. That's one condition. I'm going to have an or and then another condition. And that condition, I find out by adding 5 to both sides here. That leaves me with 2x is greater than 6. And dividing each side by 2 leaves me with x is greater than 3. Right? So there's my two conditions, but it's an or statement, right? So let's draw these guys out before we worry about the disjunction here. Let's do x is less than or equal to -1 in one spot. And then we'll do x is greater than 3 in another spot. Right? So once again, they should line up, right? 0 should be on top of 0. They should have the same scale, everything like that. But x is less than or equal to -1 is find -1 or call some spot -1. Less than or equal to is a filled in dot here, and then just shade that sucker to the left. Okay, so that's what x is less than or equal to 1 looks like visually. X is greater than 3. My scale is not going to be great because I don't know, maybe extend this. Doesn't matter. Call this 3 if you want. To be greater than 3 is an open circle, and then just shade everything to the right. Right? So, but I have an or statement here, which means the solutions have to be the solutions of one condition or the other. They don't have to be they don't have to solve both. So when I take these two lines and squish them together, I don't need to look for overlap. It's come one, come all. If you're a solution to one or the other, you're a solution to everything. So cramming these two together gives me throw in a 0 there, throw in a -1. -1's included because it's part of the top one. All of these guys to the left are included because they're part of the top one. 3 is not included because it's not included on either top or bottom, but everything to the right of 3 is, right? So I'm literally just taking these lines and putting them on top of each other and seeing what's there. And this is what's there. So when I write this, it's a disjunction because I have to put a union between these two sets. There's one set that's like all the way to -infinity starting at -1, and there's a completely disjoint set starting at 3 that goes off to the other direction to infinity. So to write this in interval notation, I would write it as parentheses with -infinity, goes up to -1, and since -1 is included, it's a bracket. Then I union that with, it's a parenthesis here on the 3 because the 3 is not actually included. It goes off to infinity, and so in interval notation, I just kind of drew over it. I don't want that. In interval notation, that's my solution. So that's what these solutions look like. All right. Let me just clear this out again. So let's look at an example here. John is hired by a taxi service and is given the choice of payment. So there's plan A. Under plan A, he gets $600 plus $12 per hour for, I don't know, monthly payment or something like that. And then plan B is that he just gets $24 per hour. And so then the question is, for what number of hours worked, I guess per, I don't know, week, month, it doesn't matter, who cares, is plan B better than plan A? Right? So that's our question. That's what we want to figure out. Essentially, what they're at, they give us some information. They give us two plans, and we want to figure out at what point is plan B better than plan A? Right? That's what we want. Plan B greater than plan A, right? Or the income earned from plan B, we want to know when that is greater than the income earned from plan A. So I want to write expressions for the plan B and plan A income, right? Income from those. The income from plan B is just $24 per hour. So I'm just going to write it as 24 multiplied by X, where X is the number of hours worked. Right? And we want to know when that's greater than plan A, which is a flat $600 plus $12 per hour, so 12 times X. Right? Now, obviously, if you wanted to shyster the system, you just don't work any hours and you get $600 for doing nothing, right? But that's not the question. The question is, how do you maximize, or at what point do you choose plan B as the better pay scale? So I just have to solve this, and it's not too bad. I'm just going to subtract 12x from both sides. And 24 minus 12, 12 again. Right. Divide each side by 12. Let me move this up just a tad bit here. Divide that by 12. Divide that by 12. I get x equals, and that's what, 550? Yeah. Oh, it's not an equals. It's a greater than, right? So at around 50 hours per whatever it is, week, month, whatever time period, he's going to want to start switching over to plan B instead of plan A. Okay. All right, and that wraps up section 1.6. So let's dive into section 2.1. 2.1 starts with, well, it's increasing, decreasing functions, and it's also dealing with piecewise functions and applications of those. Right? So an increasing function is we would say on an interval, a function, so some x value starting and stop point, a function is increasing if from left to right, the value goes, the y value or the function is greater, it grows, whatever you want to call it, increases. I don't know how to not use the word increases, but you know, increases, goes up, right? Okay. And then on the other side of that, then the decreasing function, and a function may increase and decrease on different intervals, so you have to kind of take it. That's why we define it on an interval. So on an interval, a function is decreasing if from left to right, it decreases or goes down, right? So what we mean by that is if I have some function, simple function, like just a linear function like this is increasing. Because as I look at it from left to right, it goes up, right? This one is decreasing because as we read it from left to right, it goes down. Okay. And like I said, some of these functions may have intervals where it does both. So I might have some function that does this, right? So now I would say between however far it goes, if that's forever, so that'd be like from negative infinity, But up to this point right here, this function is increasing. But then between this x value and this x value, the function is decreasing. It goes down. But then, so decreasing, and then it goes up again, so increasing, right? So this one increases, then decreases, then increases. And a lot of times we're interested on the about the interval in which these are increasing or decreasing. So let me still a plot here. There's one. It's a good one. Maybe. Can I steal it? Yes, I can. There we go. There we go. Oh, that's a terrible one because it's that stupid see-through crap. Okay, give me a better one. Sorry, let me just get. All right, this one's good. Maybe. Yep, that one's good. All right. So if I have some function that I'm going to plot on this thing, all right, let's say it goes off forever. It does something like this. And then goes off forever that way. Right? Now, we might be asked this question. What intervals is this function increasing or decreasing? Okay. So the intervals are the x values. So all I have to do is identify where this thing goes from increasing, which is increasing here, and it's decreasing here. That change happens when x is -2. So it's increasing. Since it goes forever, and we assume in that direction forever in the negative direction, then I would say it's increasing from -infinity up to -2. And then it decreases between -2, and it looks like I tried to make it 0. So to 0. But then it increases again, right? And so I would, on my increase, I'm just going to union this with also between 0 and infinity. Now notice I'm using parentheses because I don't want to throw a bracket in there because it's not increasing at 2 anymore. It's the end of the increase and the beginning of the decrease. So you can't say it's one or the other. And so it's not included in those intervals. But these are the intervals in which we have increase and decrease on this function. Now, when we have a function that looks like this, let me see if I can just get my black markings away. Ah, that's beautiful. No, not you. Bye and bye. All right. So something like this, I'm just going to go ahead and just kidding. I'm going to go ahead and erase some stuff for a second to talk about this again. Apparently I can't erase those words, but I can delete them. All right. So if we're looking at this, the very top that I just mentioned right here, where it's neither increasing or decreasing, that is the maximum of a little, kind of a little hill there, right? It's not the maximum of the entire function, but it is the maximum of its little local area. And this thing right here is called a local maximum. Right? And a local maximum is just a, like the peak, right? The peak of a, local hill. Right. For any of you that have gone on a hike, sometimes you hike up to a little peak, and that's the top of, you couldn't go any higher walking in any direction, but there may be a mountain over there that's bigger bigger or higher than where you are, but for where you're at the top of the mountain that you're at, and that's what this is the local maximum. On the other side of this, we had this little point here that was not included. And this is neither increasing nor decreasing, but it's at the bottom of the trough. And so this is called the local minimum. Which is the, the bottom of a trough, or whatever you want to call it, right? That's what it is. It's just that little tiny bit where you're at the bottom of something, and in either direction, you'd have to increase in the positive direction, but if you turn around and try to go backwards, it's also uphill for you, right? That's your local minimum. Okay. If you have plural of them, if you have more than one, then the plural of maximum is maxima, right? And then the plural of minimum is just minima. And you can have many locals, right? Let me grab that graph again, maybe make it big. That might be too big. I don't know, it doesn't matter. But if I have a graph that looks like this, there we go. Then I have a lot of local maxima. There's one, there's a maximum, there's a maximum, there's a local maximum. These together are the local maxima. And then, of course, we also have a minimum, another minimum, and these together are the local minima. Min, that's an N. Get that. Minima. Right. There's more than one of them. There they are, right? Oh, there's another one I missed. It's right here. Yoink. Also a local minimum. Okay. So I have those. I've got local minimums, local maximum. They're, the troughs and the valleys, things like that. Okay. Let me see here. They also, in your book, instead of calling them local maxima, they also call them relative. If you have to go into calculus, though, you're gonna see those called local instead of relative. But either way, relative maxima, relative minima. Okay. All right. The last kind of movement that we might have in a graph like this that we would describe is constant. And so constant means exactly what it says, unchanging. So as I read this from left to right, if I don't go up and I don't go down, I'm just steady, that's constant, right? And so you might have a graph that is constant everywhere, but you also might have something that, just goes constant for a minute and then does some weird stuff, right? But between these two values, this is constant to the best of my, writing on a tablet abilities. Okay. All right. So if I have, let me grab, there's a picture up here. I'm gonna find it. Just a couple of pages, maybe. There we go. I'm gonna steal this picture from our book and throw it up here. So we have this picture. It's a graph. I wonder if I can erase part of that picture. I doubt it. Nope. All right. But I've got this graph, right? So then where is this graph increasing, decreasing, and constant? Well, it's increasing wherever it's going up, and that happens one place. That's right here. Between the, I just drew over it, but that's the x value is 3, and then the x value of that top of the hill is 5, so it's increasing between 3 and 5. Where is it decreasing? Well, it happens twice. It happens over here, and then it happens over here. So it's decreasing from, and this arrow indicates that it's going on forever. So it would be a decrease from negative infinity up to the x value here where it stops decreasing, which they've got listed as -1. Try not to draw over what they've got there. Yoink, right? But then it decreases again, starting here at 5, and it goes off forever. So my interval of decrease is unioned with from 5 to forever. Right? Where is it constant? Well, that's just between these two bits right here. So that's between -1 and 3. And there we have it. Excuse me. Okay. I'm going to just clear this real quick. And still this. This is an example out of the book. Okay. We have two nurses, Kiara and Matthias, drive away from a hospital at right angles from each other. So one's driving in one direction, the other one's driving at a right angle from that. Kiara, let's say Kiara is driving this way and her speed is 35 miles per hour. And then Matthias's is 40 in this direction, right? So we want to express the distance between the cars as a function of time. So we're going to call that function d of t, where d is the function and t is the variable of time, right? So I have let's see here. We're assuming that they start. It doesn't say this explicitly, but we're going to assume that they start here at the same time, right? So if they start there at the same time, Kiara is going 35 miles per hour. Not that this really matters. I'm going to omit that from my equation here, but the distance, right? If she ends up some unit of time later here and Matthias ends up some unit of time here, the distance they're looking for is that straight line distance between the two of them, which is the hypotenuse of a triangle. And so you should know then that the distance here is that square root of x squared plus y squared. Or we've seen this as the distance is the square root of like the x minus the x naught value squared plus the y minus the y naught value squared. But in this case, we're calling x naught and y naught 0, 0. We're going to call this the origin where they started, right? Which then simplifies into what we had right here anyway, right? So I don't know what her position is at any given time, but I know how fast she's going. And so I really kind of do know her position. As a function of time, it's going to be 35t, where t is in hours. So I square that value. And I do the same with Matthias's, but her speed is 40t. So her speed is 40, so her distance will be 40t. If I square that, there I have the distance between them at any given point in time where t is given in hours. Okay. All right. Now, part B here says find the domain of the function. Well, the domain could be anything, because if I square it, whatever that t is, even if it's negative, I square it, it goes positive, but that doesn't really mean anything in the context of this problem. So we would say that our domain, since they're starting at that point here, would be from 0 to presumably infinity. I don't know how far these roads go. The real domain, the real problem, the real world domain would be however far they go before they can't go on these roads anymore. But we don't know that, so their domain here is just going to be from 0 to infinity. Okay. All right. This next one here. There we go. Okay. Clear this out a little bit. Up to this point in this class, we've only really dealt with nice functions. We've dealt with linear functions. We've shown some things like square root, x squared, x cubed, things like that. We haven't played with them a lot, but every once in a while, and I showed you one of these earlier, but every once in a while you get some function that might just do some weird stuff. It might look like this, and then all of a sudden bounce and do something else, and then just turn and do that, and then go off like that, right? You'll see a lot of this if you go into electrical engineering, a lot of weird signals that come through. But this can be defined, or you can express this by using little bits of functions in each little interval. So what that is called is a piecewise function. Because you're going to create this graph piece by piece, piecewise, right? And so piecewise function is really just using many, however many, it doesn't matter, but functions defined on intervals to create a graph or a complicated function. That is what piecewise is. It's just saying, hey, this is too complicated to get some big ugly function to describe it, so I'm just going to do it in pieces, because it's easy to describe, something, a straight line over here with one function, and then a parabola with a different function, then constant, and then some other linear type function. It's easy to do that just piece by piece. If I had to come up with one equation that described the motion of this graph, I could do it, but not until like 5 classes after calculus, and it's going to be humongous and ugly, right? So let's look at what piecewise functions we can create here. A lot of them look like, before we graph it, look like this. Let's say I have a function, and to do a piecewise, you're going to throw a huge bracket and then just define each part of the piece with some function. So I might have, like, say, x plus 1, and then I have to have the interval on which this is valid. So sometimes you'll see if, or sometimes you'll see on, or sometimes you'll see for, whatever the case may be. But here, let's say if x is less than, let's say, -3, and then let's call it I don't know, x squared. If x is between or equal to -3, and let's just say, I don't know, 0. Now let's go 2. And then let's just say it's constant after that. If x is greater than or equal to 2. So over here, I have the entire x-axis just broken into pieces, but it's all there. Anything left of -3 is the first one. Between -3 and less than 2 is the middle one, and then anything greater than or equal to 2 is the last one, the bottom one, right? So this is a piecewise function, and you might be asked to evaluate this at some values. You might be asked, what is f of 2? Right? So you have to come over here and see where this is valid. It's not in the middle because 2 is not less than 2, and it is greater than or equal to -3, but it doesn't fit with this less than 2. It does fit with this bottom one, though. And so f of 2 is simply that constant value of 5. F of 0, we have to see where 0 is valid. That 0 happens to be valid on this middle expression, that middle interval. So f of 0 is, plug it into this part of it, 0 squared, which is 0. Get some more values. Let's go f of -1, just see where that is. F of -1 belongs in that middle interval. And so that's -1 squared, and that's 1, right? F of -4. -4 is the top interval because that -4 is less than -3. And so I plug it into the top. That's -4 plus 1. And so that is -3. So it's a complicated little set of instructions. They're not that complicated, but you do have to watch out for where your x value is valid before you pop it into the function and try to get a value out of it. What does the graph of this thing look like? Well, let's take a look. Do I have a graph in my? Yes, I do. Nice. And what I would do to graph these, for the first couple of times, if you have colored pencils or pens or whatnot, it's nice to come in here and say, well, my graph gets changed when x is -3. So I'm just going to create my little areas at -3. Something happens to the left of it and something different happens to the right of it. And then again at 2, something changes. And so those are my pieces. I have one piece to the left of -3, one piece between -3 and 2, and then a different piece from 2 onward, right? But the function x plus 1 over here is, it's a straight line. We know that. It's y equals mx plus b. And it would be, I'm going to draw this and then I'm going to erase a bit of it. This line looks like this. If it were valid everywhere, it has an intercept of 1. It has a slope of 1, so it goes up off in this direction and that direction, right? So that's the graph of x plus 1, but it's not valid everywhere. It's not valid in this section, and it's not valid in this section. So I need to get rid of it. And in fact, it's not even valid at -3. So I need an open circle here at -3 because it stops there and is not valid there. So I'm going to erase this stuff. It doesn't belong over there. I erase my partitions here. Right. But it's going to go up to and then not include -3, so I have an open circle there. Right? And then in between these two values, between -3 and 2, I have a different function. It's x squared. I know what x squared looks like. If x is 0, x squared is 0. If x is 1, x squared is 1. Same with -1. If it's -2, I go up to 4. And so I would be here. So my function looks like this. Should be a parabola. Oh, I missed. Darn it, that's so sad. And I'm making it worse. But it should look something like this, right? It's a little less V-shaped, a little more round. But it goes off forever up in this direction. I mean, not forever. It's going to end up hitting this point up here at 9. So I don't know how far, but I'm going to call that 9. And it's going to be valid there because of this less than or equal symbol there. But it's going to be an open symbol or an open circle over here. Trying to make it more open there because of the strict inequality that happens at 2. Right? And then on the, let me do a little erasing because as I do this and explain it, it starts to look a little hairy and ugly. Get rid of this interval perhaps, make it look less ugly. But on the right, from here on out, it's going to be a different function again. It's going to be just 5. It doesn't matter what x is, it's always going to be 5 up here. So it's valid at x equals 2. So it's a closed dot. And then it's just that forevermore. Right? So if I want to take a look at this, I'm going to clean up just, oh, that's black. That's not cleaning anything up. Clean up my red. Right. If I want to look at this, it's literally, I don't know if black's going to help or make it worse, but the function is then just that. With that guy there, a big open here. Yeah, I don't know that the black is adding any value to this, but that's my function. Right? And it's a piecewise because I described it with, in this case, 3 different pieces. All right, these ones are oftentimes confusing. There's a couple of examples on the book. There's another, if you have questions, of course, ask me. There are other resources if you want. There's YouTube videos. Khan Academy has piecewise function videos. But yeah, you can always ask me. I'll be glad to draw up some more if you want. But for now, let's just keep going here. Okay. Let me do this one. This one's not terrible. Well, I mean, it's kind of bad, which is why I'm doing it, but it's not terrible. So we want to graph. I have a function, a piecewise function, f of x equals, and it's only 2 pieces, but this is x squared minus 4 over x plus 2 for x is not equal to 2. X is not equal to negative 2. And then it's defined as simply being 3 when x is 2, right? And you can see why they chose to define it differently at x equals negative 2, because if x is negative 2, I get a negative in the denominator here, right? And we don't like to see that. So what I can do is take a look at what happens with this x squared minus 4 over x plus 2. I can do a little bit of simplification here, because x squared minus 4 is equal to x plus 2 multiplied by x minus 2 if I factor that guy out. And if this is over x plus 2, then in fact that simplifies down to just a straight line, right? So it looks a little bit hairy, but it simplifies down to x minus 2. And this is, of course, as long as x wasn't 2 itself, negative 2, right? Sorry, this should be negative right there. Because if it is negative 2, I can't cancel out 0 and 0. The whole thing is in the garbage if x is negative 2. But if it's not negative 2, it's just this straight line, y equals mx plus b, slope of 1, intercept of negative 2. But because I've defined it only, well, for every value except negative 2, essentially, this is the line that goes through negative 2. because that's my b value. It has a slope of 1, and so it's valid everywhere except at -2. Okay? So it's a straight line everywhere except that one spot. I could probably pull the ruler out and make that look straighter, but that doesn't matter. It's that line, right? But what is the value when x is -2? Well, we've defined it up here as 3 when x is -2. So we just have this jump right up here. It's discontinuous, but that's okay. We have that point, and so my graph looks like that when it's all said and done. It's this straight line everywhere except at that one point where it's been defined to be 3. So something that we see again in electrical circuits a lot, but we see it in other places quite a bit, is called the greatest integer function. And they write it like this. Sometimes you'll see it different, but I need a marker. In brackets, and then an x, and then brackets, right? So you might see this, the function of x being that bracket, x bracket, that's the greatest integer. And what it means is, if this is the function, oops, drag it off, the function that returns the greatest integer that is less than x, less than or equal to x. So a lot of people would also call this a truncator. I don't know if the book calls it that, but I also don't know if it's OR or ER, but it's truncator, right? And for example, if I have, like, say my f of x is defined as that greatest integer, x, then if I plug in something like, say, 1.21536, that is the greatest integer, 1.21536. It's the greatest integer, the very largest number that is an integer, but is not larger than this number. That number is 1. That's why we call it a truncator, because it just takes all of these decimals, chucks them in the garbage, and it's just the integer that we started with at the very left, right? So f, in this case, let's say f of whatever, 1.7, right? The greatest integer is the largest number, the largest integer that is not greater than this, and therefore that's also 1. Okay. F of 1, greatest integer, is 1. Okay. The f of 3/2, also 1, right? Because 1 is the largest number, the largest integer that's not greater than these numbers that I've put in there, right? So if we see things like f of pi, the largest integer that isn't greater than pi, that's 3, right? So it's a way of truncating things. We can graph this, and the idea behind this greatest integer is that this is also a piecewise function, but it's infinitely many pieces, right? So if I want to graph this, do I have a graph still? Yes, very nice. All of these values over here, 1.7, 1.2, 1 itself, 1.5, they all ended up being 1, right? Which is to say anything including 1 that is greater than 1, but not 2, gets all returned down to 1. Once you get to 2, f of 2 is 2, f of 2.1 is 2, f of 2.2, 2, 3, 4, all the way up to, but not including 3, right? And so it creates sort of a step graph like this. And it goes the other way as well. F of 0 is 0. F of 0 point anything is 0 until you get to 1. And then we see stuff like this happening. Right? And it goes in the direction, this other direction as well. Right? And so that, oh, they've got it right here. Thank God, because I don't want to write this. Is infinitely huge piecewise function that looks like this. Right? They've got these dots up at the top because this keeps going on forever. -4, -5, -6, and these ones go on forever that way as well. So it's an infinitely long string of a piecewise function. Sometimes you'll see this bracket notation is not universal. Sometimes you'll see it as a double bracket, like that. Sometimes you'll see it as just the bottom part. And this is also called the floor function. Yeah, doesn't matter. I think in the book, I can't tell because I'm on a weird screen. I think they're using this, but they might be using this because it's a little fuzzy. All right, let's look at this. Let me get there. Okay, we're going to look at 2.2. 2.2 is the algebra of functions. If I can spell today. What the heck? Algebra of functions. Put my S there, please. Okay. Good. All right. So we've seen addition, subtraction, multiplication in just regular numbers. We're going to then kind of take these and do similar operations with functions themselves, right? So some of these are very easy to understand. So for example, if I have one function, let's just call it f of x, and give it a value of whatever, x plus 2. And if I have some other function, g of x, then let's call it 3x plus 1. Right? Now, if I take f of 2 and I add it to g of 2, I can rewrite f of 2 as the function f with 2 replaced. So that's 2 plus 2 plus, and then g of 2 is 2 into that one. So 3 times 2 plus 1, right? And I can solve this down into a number, right? 4 plus 6 plus 1, which is 7. So this is 11, right? But we introduce a notation now that is, instead of f of 2 plus g of 2, I'm going to write this as f plus g evaluated at 2, right? And these things mean the same thing. F of 2 plus g of 2 means the same thing as f plus g of 2, but I'm now adding functions together instead of evaluating the functions and adding the results together. So let's take a look at what I mean by, say, f plus g of x first. F plus g, and this is why we would want it, is because sometimes we don't know what these values are. But f plus g of x would then mean literally f of x plus g of x. But that's just x plus 2 plus 3x plus 1, and I can simplify this down. This becomes 4x plus 3. But it's a new function. This we're just calling the function that came from adding f and g together, and the input variable is still x, right? But if I take this f plus g of x, which I've now just defined to be 4x plus 3, plus g, and evaluate that at 2, I should get the same value. Let's take a look. 4 times 2 plus 3. 4 times 2 is 8, plus 3 is indeed 11. And it's probably easier to evaluate that than it was to have evaluated these separately and then added them. Not a lot easier in this case, but half a step easier, right? So that's what we mean when we have f plus g of x, is literally just add those two things together. Let's use f of x here equals 2x minus 1, and g of x equals 3x plus 4. Okay. So I can do the same thing with subtraction. Again, this is one of the easier ones to understand. F of x minus g of x is going to be a new function. It's all going to be some x, polynomial in x. But we're going to call this f minus g of x. It's just the function whose input is x that we got from subtracting f minus g, right? So if I take f of x minus g of x, I can then just take literally 2x minus 1, and I don't know where that's coming from. Get out of here. Not ready for it. And minus g of x. So minus off the entire 3x plus 4. Right? So that is to say I get 2x minus 1 minus 3x minus 4. Or negative x minus 5. And so if I want to evaluate something like, say, f minus g of 2, let's say, I can plug 2 just into this equation. That is to say I have minus 2 minus 5, or negative 7. But I should get the same result as if I had come over and said, take f of, 2 minus g of 2. F of 2 is 2 times 2 minus 1, and I'm going to subtract off g of 2, but g of 2 is 3 times 2 plus 4. Scooch this page up just a little bit. I should end up with negative 7, right? 2 times 2 is 4, minus 1. This minus distributes to the 3 times 2 in 6, so minus 6, and it distributes to give me minus 4. You can see here 4 minus 1 is 3, minus 6 is negative 3, minus 4 more is indeed negative 7, right? But again, it was easier to have plugged this into the function that we've already subtracted. And if you have to do this 100 times, you'll want to pick that one that's even the second easier. It'll take you a few minutes of your life that you don't have to be spending doing this problem, right? Okay. Those are the two pretty easy to understand ones. The next two are still easy conceptually, but they get a little bit more involved. So let's say I have two functions. F of x equals x plus 2, and g of x equals x minus 3. Now, f times g. I'm going to write it here, f of x multiplied by g of x. We would write the result of that as f times g of x. So f of x I can write out as x plus 2. G of x I would write out as x minus 3. And I would FOIL these together, which gives me x squared minus 3x plus 2x, and then minus 6. Right? And I can simplify this to be x squared minus an x minus 6. So that's what I'm saying f times g of x is. And once again, I should be able to evaluate something that says, say, f of, I don't know, 2 multiplied by g of 2 should give me the same thing as f multiplied by g, that polynomial evaluated at 2. So let's try it. F of 2 would be plugging 2 into f of x. So I'm just going to write it. 2 plus 2 is 4. G of 2 is 2 minus 1, so that's negative 1. So in the end here, I get negative 4. On the right-hand side, f times g evaluated at 2 is plugging a 2 in here, so 2 squared minus 2 minus 6, which is 4 minus 2 minus 6, or 2 minus 6, which is indeed negative 4. And they're the same, they check out, right? Okay. So again, not terrible, right? It's just the two things multiplied together. When I get to this division, however, let's say f of x is 2x plus 1, and g of x is x minus 3. F of x divided by g of x, which will work out, can then be written as f over g in a parentheses of x. And again, they should be the same thing. So f of x is just 2x plus 1. G of x is x minus 3. There's not a whole lot that I can do to simplify this. So this is just my value. And there's no point in evaluating these separately, because evaluating f over g of x is evaluating f of x and then dividing it by g of x. But this is valid only when g of x is not 0. Right? I can't have g of x being 0, otherwise my denominator is 0. Therefore, x cannot be 3, right? It can't be, because if I try to plug in a 3, I get a 3 in the denominator. Can't do it, right? Okay. All right, let's see here. I'm going to clear this out. Maybe. There we go. Try to get to the top of my whiteboard. Okay. All right. Let's look at one that's interesting. Here we go. I have f of x equals, let's say, x plus 1, and g of x equals the square root of x plus 3. Okay. Now, I want to find each of those things, so I'm going to find f plus g of x. So that one's pretty easy. It's just these two things added together, x plus 1 plus that square root of x plus 3. And I can't simplify, so it's just that. F minus g of x is f of x, but minus g of x. So it's that. Okay. F times g, so f times g of x is the product of these two things. So I would write it like this, in parentheses, x plus 1 multiplied by the square root of x plus 3. Right? And you could simplify, maybe, it's not necessarily simplifying, but you could distribute the square root of x plus 3 through that binomial of x plus 1, but I wouldn't bother. Okay. And then f divided by g of x is equal to f of x divided by g of x. We might be asked about the domain of each of these, right? So the domain is limited by the square root mostly, right? The square root x plus 3, x has to be greater than or equal to 3. Sorry, negative 3. Otherwise, you get a negative under the square root, right? So you should be able to convince yourself that that's true. If not, we've done, domains of square roots before, set the inequality and solve it. So each of the first 3 of these is bound by that domain restriction. X has to be greater than negative 3 for all 3 of these. But this last one is not exactly the same, because these first ones, you can have a 0. If negative 3 is plugged under the square root, I get a negative 3 plus 3 is 0. Square root of 0 is 0. That's okay. I'm fine with that. But what I'm not okay with is when the square root of 0 being 0 ends up in this denominator. And therefore, I have to exclude negative 3. And so this one has a little bit more restrictive domain of x has to be greater than, strictly greater than negative 3, right? So watch out for things like that, that domain restriction based on fractions or square roots, things like that. Be mindful of where those end up. Okay. All right, and then we talk about something, and I can't recall the purpose of this class, if you're going on to calculus or not after 124. I seem to think that you wouldn't. Otherwise, you would have been in 126, but I might be wrong. I probably should pay better attention to that type of stuff, but I haven't, so sue me. But something that you'll see in calculus a lot if you end up there, and some of you may, depending on what you do, is something called the difference quotient. And a lot of you will end up perhaps in business calculus, which you'll still see this. But the difference quotients are this. Let me still this picture because I like it. All right, on the graph, we're going to look at this graphically for a bit. On this graph, we have 2 points, right? I have some x value and the y value associated with it. We're just going to call f of x, starting at some random x point, right? Or x value, some input value. But if we move to the right, however far we move to the right, we're going to move to the right h units. If we move h units to the right, we end up at x plus h, and we should find a point on the graph that is x plus h, comma, and then the function evaluated at x plus h. Okay? Very general terms here. We don't know what x is. We don't know what f of x is. We don't know what x plus h is. We don't know what f of x plus h is, right? But we can create a secant line between those 2 points. That is a line that goes through those 2 points and kind of cuts into the graph, basically, right? So I have that, right? And the difference quotient is defined to be this. f of x plus h minus f of x over, and I'll write it out, and I'm going to simplify it in a second, but x plus h minus x. And it's very simple. If you cannot remember this function or this quotient, it's very simple to remember just y2 minus y1 over x2 minus x1. Right? This is just the grown-up version of that, right? Where I have x1, y1, x2, y2. It gets rid of this notion of a second x and a second y, and it just turns it into specifically this far away, or h units away from my first x is my second one, right? But y2 is this f of x plus h, so that goes there. Minus y1 was the original f of x, and then my x2 was x plus h minus my original x, which was just x. But if I clean this up a little bit, let me erase this guy here. I have an x and a negative x in the denominator, so that simplifies out. And I end up with f of x plus h minus f of x. And in the denominator, the x's cancel out and just leave me with h. Right? So this is called the difference quotient. Okay. And as you might guess, because I wrote that y2 minus y1 over x2 minus x1, that is the definition of a slope. And so this tells you essentially the slope of the line between the point x and f of x and some point h units to the right. So, and x plus h, and then the function evaluated at that point. Okay. Now, this is what Isaac Newton started dealing with when he invented calculus. And he looked at this equation and he worked with it and he worked with it. And he said, man, this equation sucks when it gets into harder formulas and things like that. And so he said, screw this, I'm going to invent calculus. And he did. And Leibniz kind of did the same thing. But for now, this is what we have. This describes essentially that average rate of change between two points. Right? So let's play with it a little bit. Let's use it. Let me scooch this up. We're going to use that. And we want to evaluate the difference quotient for the function, let's say f of x equals 3x minus 4 between, not just the general one, not between any two values, right? So we want to evaluate the difference quotient for the function f of x equals 3x minus 4, which means plug this thing in there and then simplify it and see what happens. So there's a few parts to this thing that you can make life easier if you just break it down. There's this f of x plus h. There's f of x. And then h is just h, right? So it's really these two bits. But I already have this bit right here. F of x is given to me. F of x is 3x minus 4. F of x plus h is just putting in x plus h in for the x in that term, or that equation, that function. So this is then 3 multiplied by, instead of x, now it's x plus h minus 4. And I'm just going to worry about what f of x plus h is. So I'm going to take this 3 and distribute it through. This turns into 3x plus 3h, and then minus 4. And so I have that bit of it. And now if I want to create the entire difference quotient, it's f of x plus h, which I have right here, minus f of x, so minus the original function, 3x minus 4, and then this whole thing gets divided by h. And then the majority of playing with the difference quotient is cleaning it up. So I'm going to take and distribute, I'm going to scooch this up a little bit. I'm going to distribute this negative through the parentheses, yoink, yoink, and I will clean this up a little bit, still have my 3x plus 3h minus 4, but now it's minus 3x and then plus 4 up in the numerator. And that's all over h still. Okay. But I can see that 3x and negative 3x will cancel each other out. I have a minus 4 that's going to cancel out a positive 4. And this happens a lot, you're going to see a lot of stuff just disappear on you. The only thing I have left in the numerator is 3h. And the only thing in the denominator is h, because h is a product in the numerator and the only thing in the denominator, I can cancel it. And my final answer is 3. And if you've taken calculus before, you would have guessed that way before all this work happened. You could just look at it and say, bam, it's going to be 3. Right? But if you haven't, then you'll get there. Okay. Let's look at I hate to say harder, and I also hate to use uglier, but that's exactly what we're headed into. So let's look at a harder, uglier one. Let's say that we have f of x equals 1 over x. Okay? And we want to find the difference quotient. Okay. Well, again, that difference quotient, I'll just write it for our reference here, is f of x plus h minus f of x all over just h, right? Okay. So that means I'm given f of x. I don't have to do anything for that. So this f of x plus h is the one thing that I really have to do any work to find. So f of x plus h isn't that hard. It's just that 1 over, but instead of x, now it's x plus h, replacing x plus h in for the x. Right? So then I just have to plug and play. F of x plus h was this. It's given to me. Well, not given to me. I just found it. But it's 1 over x plus h minus f of x, so minus the original function, which is 1 over x, right? And then all divided by h. That's the difference quotient. Of course, 90% of this game is cleaning it up and simplifying. So I've got a complex, not complex, but I call it ugly, but a complicated fraction. And so to combine the difference of the two fractions up in the numerator, I'm going to multiply by the common denominator. Or I'm going to get the common denominator by multiplying what's missing. So I'm going to multiply this right one by x plus h. Over x plus h, and I'm going to multiply the left one by x over x. That way my denominator is now x times x plus h. And so if I clean this up just a little bit more, a couple steps, the left fraction becomes x over x times x plus h, which is what I wanted. Minus, I'm going to write this as x plus h over x times x plus h. Once again, that's what I wanted. I wanted those two denominators to be the same so I could combine them. And then this is all over h. Give myself a little bit of room here by scooching up. Now this negative is in front of the fraction, so I'm just going to distribute it to the x and to the h. As I turn this into a single fraction in the numerator, this becomes x minus h all over x times x plus h all over h. And I can think of that h as being just an h over 1 if I want. That gives me a fraction over a fraction. But I can still simplify stuff because x minus x is gone. That leaves me with just a minus h over this x times x plus h. And then that's all over this h over 1. That's as much as I can simplify that numerator, but now I have a fraction divided by a fraction, so I'll take that bottom fraction, flip it, and multiply. So I'll write this as negative h over x times x plus h multiplied by 1 over h. Flip that denominator. My h's cancel out. And so if I do the final simplification here, that ends up being negative 1 up top, and then x times x plus h in the denominator. And that's my simplified final version of this. All right. Let me do one more of these. Sometimes people get a little overwhelmed with these, and that's understandable. So let's do one more. Again, we're going to find the difference quotient. Maybe, there we go. Find the difference quotient of, and we have f of x equals, let's go 2x squared plus 5x minus 1. So it's bigger because now there's an x squared. So again, for reference, we're looking for f of x plus h minus f of x all over h. Right? Okay. And f of x plus h, that's the only thing I really have to take a minute to find is f of x plus h. So f of x plus h is 2 times x plus h squared. Oops, my squared goes here. Plus 5 times x plus h minus 1. I'm going to go through and take the time to simplify this because I'm going to end up simplifying everything in the end. So I'm going to expand out x plus h squared. That's going to do this on paper if you don't see it, but this is just going to end up being a 2 multiplied out in front of x squared plus 2xh plus h squared. And then plus, I'll just distribute the 5 now. So 5x plus 5h. And then minus 1. And then in this 2, I'm just going to take and distribute the 2 through these guys. So this is 2x squared plus 2xh. 4xh. Because I'm multiplying by 2. And then plus 2h squared. And then plus 5x. And then plus 5h. And minus 1. Now, if there's anything else to simplify here, I'd want to do it. It doesn't look like it. I've got an x squared, an h squared, an x, an h, and then an xh, right? So that's it. That's my f of x plus h, expanded all the way out, which is fine because I'm going to take this guy, and I'm just going to say that is this part of the function, of the quotient, right? So from here, I'm then just going to subtract the original function, so minus the function, which was 2x squared plus 5x minus 1. And then this whole big bastard, this whole big thing over an h, right? So it's big, it's ugly. That's what we've got, right? So I'm going to take this the negative and distribute it through. And this ends up being I've still got 2x squared plus 4xh plus 2h squared plus 5x plus 5h minus 1 minus 2x squared. And you'll start to see some good things happening here. Minus 5x plus 1. Those good things are that a negative 2x squared and a positive 2x squared are going to cancel. A negative 5x and a positive 5x cancel. A 1 and a negative 1 cancel. And stuff just starts flaking off of this thing. All of this junk is still over h. But with what I've simplified, the only thing I have left are these two terms. Up top, 3 terms, sorry. I've got 4xh plus 2h squared plus 5h, all divided by h. Now what's awesome about this is there's an h in every single one of the numerator's terms, and so I can factor out an h. That leaves me with 4x plus 2h plus 5. Why do I want to do that? Because I can't cancel anything with that h in the denominator until it's a factor. Now that it is, it cancels. And my final answer here is 4x plus 2h plus 5. Right? Not the worst thing I've ever had to get through, but it's kind of a long one. So thank you. That wraps up 2.2. And again, if you have any questions on any of this material, talk to me about it, email me, put something in the discussions, but make sure you understand this one way or another, and I will see you guys for the next one.